Welcome to today's paper reading. Today's paper is titled, Learning 3D-Aware GANs from Unposed Images with Template Feature Field. This paper was published on AR14 by Xinya Chen and colleagues from Zhang University. This abstract introduces a method for learning 3D-aware generative adversarial networks, GANs, from unposed images. The approach involves on-the-fly pose estimation using a Learn Template Feature Field, TeFF. In addition to the generative radiance field, the generator learns a field from 2D semantic features, sharing the density with the radiance field. This framework enables the acquisition of a canonical 3D feature template, facilitating efficient pose parameter estimation on real data. Experimental results show that this method outperforms state-of-the-art alternatives on various challenging datasets, both qualitatively and quantitatively. Figure 1 illustrates the proposed method for performing on-the-fly pose estimation of training images using a Learn Template Feature Field, TeFF. This approach enables the learning of complete 3D shapes from challenging datasets, including elephants, planes, and in-the-wild car datasets. In contrast, other methods often result in half or inaccurate geometry. The figure highlights the superiority of the proposed method in generating accurate and complete 3D shapes. In this presentation, we will introduce three key concepts: 3D-aware generation, semantic features, and pose estimation. 3D-aware generation involves creating realistic 3D models and high-quality renderings for interactive applications. Semantic features focus on object recognition, scene understanding, and feature extraction. Pose estimation is crucial for tracking human body movements, recognizing gestures, and analyzing motion. 3D assets are crucial in various media formats such as video games, movies, and computer graphics. Designing these 3D assets manually is costly and time-intensive. Learning generative 3D models from 2D images offers a promising solution to reduce this effort. This approach is particularly beneficial as it can generalize across different object categories. Figure 2 presents a qualitative comparison of three 3D-aware generative models, 3DGP, POF3D, and our proposed method. The comparison is conducted under the same camera pose conditions. Notably, objects generated by 3DGP and POF3D are shown to face different directions despite the identical camera pose, which indicates issues in pose consistency. In contrast, our method successfully generates objects that face the same direction, demonstrating superior pose estimation and consistency. This comparison highlights the effectiveness of our approach in maintaining object orientation uniformity across different renderings. In 3D-aware image synthesis, the focus is on lifting the generator to the 3D space. The choice of the underlying 3D representation is crucial. Early methods like voxel grids and meshes have limitations in image fidelity. More recent methods use neural radiance fields, achieving photorealistic results but often require known camera pose distributions, such as those for human faces, cat faces, or synthetic car datasets. For unposed image synthesis, methods like Compari, POF3D, and 3DGP have been developed, but they face challenges with complex pose distributions. Figure 3 provides an overview of our method, which augments the generative radiance field with a semantic feature field to enable the estimation of camera poses of real images on the fly. This enhancement facilitates the training of 3D-aware GANs. Specifically, we map a randomly sampled noise vector to both a radiance field and a semantic feature field. By computing the mean shape of the feature field, we derive a 3D template feature field. This template field allows for efficient 2D-3D pose estimation, which is then used to guide the generator in performing volume rendering. The blue section highlights the auxiliary task of pose estimation introduced in our method. The method presented in this paper involves augmenting a 3D-aware GAN with template feature fields, TeFF, to facilitate learning from real-world images without requiring camera pose distributions. The core of this approach is the joint learning of both a generative radiance field and a semantic feature field. This joint learning allows for the extraction of a 3D template feature field, which is then used to estimate the camera poses of real images in real time. This innovative method addresses the challenge of camera pose estimation by leveraging semantically aligned features across different instances, thereby enabling more accurate and efficient pose estimation. Figure 4 illustrates the process of camera pose estimation. The method involves discretizing the azimuth theta and elevation phi angles to render the feature field from various camera poses. Phase correlation is then employed to estimate the scale and in-plane rotation within the 2D image space. Each render template is warped based on these estimations. The mean square error is computed between the warped rendering and the real feature to derive the probability distribution function of the camera pose. Finally, the camera pose is sampled using inverse sampling. Figure 5 illustrates the camera model used for pose estimation. The camera pose is parameterized by psi equals theta, phi, gamma, r, where theta and phi represent the azimuth and elevation angles, gamma is the in-plane rotation, and r is the sphere radius. The model discretizes the azimuth and elevation angles to perform a grid search for the best matching pose. Additionally, phase correlation is employed to efficiently estimate the scale and in-plane rotation between the real feature map and the template features. This approach allows for accurate and efficient camera pose estimation by combining grid search with frequency domain calculations. In this section, we discuss the datasets used for evaluation, the baselines against which our method is compared, and the metrics employed to assess performance. The datasets include ShapeNet cars, ComCars, SDAP Elephant, and LSUN plane, each with specific characteristics and resolutions. The baselines considered are e.g. 3D, POF 3D, and 3DGP, with specific pose sampling strategies. The performance is evaluated using metrics such as FID, depth error, and KL divergence, with different variants like FIDGT, FID360, and FIDUS to account for varying camera pose distributions. Figure 6 presents a qualitative comparison of 360-degree rendering on the SDIP Elephant dataset. Each sample is shown from 360 viewing directions, highlighting the fidelity and consistency of the rendering. The bottom right of the images illustrates the corresponding geometry. e.g. 3D, 3DGP, and POF 3D demonstrate performance in specific views but fail to maintain consistency across all 360 degrees due to incomplete or inaccurate geometry. In contrast, our method achieves 360-degree rendering with high fidelity and learns complete geometry with high quality, outperforming the baselines in both rendering consistency and geometry reconstruction. Figure 7 presents a qualitative comparison of 360-degree rendering on the ComCars dataset. The figure showcases each sample from 360 viewing directions, highlighting the performance of various methods including e.g. 3D, 3DGP, and POF 3D. These baseline methods demonstrate effectiveness in specific views but struggle with consistent 360-degree rendering due to incomplete or inaccurate geometry. In contrast, our method excels in providing consistent and high-fidelity 360-degree rendering, underscoring its ability to learn complete and high-quality geometry. This superior performance is evident in the ability to render the entire object correctly from all surrounding viewpoints, unlike the baselines which either fail to reconstruct the geometry accurately or only manage to reconstruct half of the object. Figure 8 presents a qualitative comparison of 360-degree rendering on the LSUN plane dataset. Each sample is shown from 360 viewing directions at 60-degree intervals. The figure contrasts our method with e.g. 3D, 3DGP, and POF 3D. While these baseline methods perform well in specific views, they fail to maintain consistency across all 360 degrees due to incomplete or inaccurate geometry. In contrast, our method achieves high fidelity and complete geometry across all viewing angles, demonstrating superior performance in rendering and geometry reconstruction. Figure 9 presents a comparison of the ground truth, GT, and estimated pose distributions for different methods concerning azimuth and elevation angles on the ShapeNet cars dataset. The pose distribution of 3DGP is shown to collapse to a small range, while POF 3D covers a larger range but fails to capture the multimodal distribution, maintaining a Gaussian shape similar to its initialization. In contrast, our method's estimated pose distribution is notably more accurate, as verified by the quantitative comparison of the KL divergence in Table 3, where our distribution significantly outperforms that of 3D-GP and POF 3D. This superior pose distribution is crucial for better recovering the full object geometry. Table 1 presents a quantitative comparison of various methods on the ShapeAt-Cars and CompCars datasets. The metrics evaluated include depth, FIDGT, depthist, and FIDist, e.g. 3D, 3D-GP, POF 3D, and our method are compared, with our method showing competitive performance, particularly in depthist and FIDist metrics. The table highlights the depth and FID values for ground truth and estimated data, providing a clear view of the performance differences between the methods. Table 2 presents a quantitative comparison of various methods on the SDAP elephant and LSUN plane datasets. The table includes depth 360 and depthist metrics for e.g. 3D, 3D-GP, POF 3D, and our method, as well as FID 360 and FIDist metrics for the same methods. This comparison highlights the performance of each method in terms of depth estimation and image fidelity across different viewing angles. The results indicate the strengths and weaknesses of each approach, providing a clear benchmark for future research in 3D image generation and depth estimation. Table 3 presents a comparison of the pose distribution among different methods, focusing on azimuth and elevation angles. The data reveals that the pose distribution of 3D-GP is confined to a narrow range, indicating a lack of diversity. POF 3D, while covering a broader range, fails to capture the multimodal nature of the distribution, maintaining a Gaussian shape similar to its initial state. In stark contrast, our method demonstrates a notably more accurate pose distribution, a fact corroborated by the quantitative comparison of KL divergence, where our method outperforms both 3D-GP and POF 3D. This superior distribution is pivotal in our method's ability to more effectively recover the full geometry of objects. Table 4 presents an ablation study on the ShapeAt-Car dataset, focusing on pose estimation methods. The table compares three methods, TeFF-RGB, TeFF-Gray, and TeFF, our method. Key metrics include KL divergence for angles theta and phi, and depth and FID metrics for 360-degree views and estimated views. The results highlight the performance differences between using RGB images, grayscale images, and our semantic feature-based method in terms of robustness and accuracy in pose estimation. Table 5 presents an ablation study on the CompCars dataset, focusing on the impact of different degrees of freedom, DUF, on the performance metrics. The study compares the results of using only 2 DUF, theta, phi, with an alternative that includes 4 DUF, theta, phi, gamma, r. Despite achieving a lower FIDist with 2 DUF, the generated 3D samples exhibit incorrect geometry, as evidenced by the worse FID 360 and depth metrics. This highlights the critical role of modeling scale and in-plane rotation in the camera model for accurate 3D representation. The method has limitations in modeling images with significant perspective distortion. The perspective effect is modeled by generated geometry, which can lead to failure cases. The 2D-3D pose estimation is influenced by the geometry of the instance, as the method uses mean-squared error to select the best matching camera pose. Future work will explore disentangling geometry information during the matching process. Additionally, the method does not model the articulation of the instance, which can result in different articulations being modeled in different views, occasionally leading to instances with multiple legs. Figure 10 illustrates a failure case in the 3D pose estimation process. The primary issue highlighted is the inability of the method to handle images with significant perspective distortion. This distortion is modeled by the generated geometry, which can lead to incorrect pose estimations. The method uses mean-square error, MSE, to select the best matching camera pose, which may be influenced by the geometry of the instance. This limitation suggests the need for future work to explore disentangling geometry information during the matching process to improve accuracy. The TeFF approach presented in this paper enables the learning of 3D-aware generative models from in-the-wild images with unknown camera pose distributions. By dynamically estimating camera poses, the method successfully recovers the full 3D geometry from datasets with challenging distributions. Although the results are promising, the method is limited by its use of a single feature template, making it applicable only to a specific category. Future research could explore the use of multiple templates to develop a single 3D-aware generative model capable of handling images from multiple categories. In this section, we will briefly review some key references that have contributed to the development of 3D-aware generative adversarial networks, GANs. These include the use of Deep Vision Transformer, VIT, features as dense visual descriptors, the emerging properties in self-supervised vision transformers, and the efficient geometry-aware 3D GANs. Additionally, we will discuss the advancements in neural radiance fields, NeRF, such as depth-supervised NeRF, generative radiance manifolds, and the style-based 3D-aware generator called StyleNeRF. Finally, we will touch upon various methods for image synthesis, including PyGN for 3D-aware image synthesis, Vari3D for generative vertex-based radiance fields, and Mimic 3D for 3D to 2D imitation. The runtime breakdown shows that the template rendering process takes 0.0992 seconds per iteration in the early stage, while phase correlation and camera pose sampling take 0.3898 and 0.0156 seconds per iteration, respectively. In contrast, a naive grid search method significantly increases the template rendering time to 4,423.0519 seconds per iteration in the early stage, making it impractical for training a 3D GN. An ablation study on the number of discretizations reveals that reducing the bins of theta times phi from 36 by 18 to 24 by 12 or lower worsens FID due to larger quantization steps, while increasing bins beyond 36 by 18 yields comparable results, but with increasing costs. Figure 11 presents our generated samples on the face and cat datasets, specifically the FFHQ and AFHQ datasets. The figure serves as a visual comparison of our method with EG3D and POF3D, highlighting our comparable results on the FFHQ dataset and superior results on the AFHQ dataset. The qualitative results showcased in Figure 11 demonstrate the effectiveness of our approach in generating realistic and high-quality samples, despite not using ground truth poses. Figure 12 presents the qualitative results of camera pose estimation on the CompCars dataset. The first row displays the real image I and its corresponding deno feature F. The second row shows the best matching template feature F*** operator, which indicates the estimated pose of the real image. This figure demonstrates the effectiveness of the method in accurately estimating camera poses, despite some challenges such as object articulation and partial observation. Figure 13 presents the qualitative camera pose estimation results on the SDIP elephant dataset. The first row displays the real image I and its corresponding deno feature F. The second row shows the best matching template feature F** operator, which indicates the estimated pose of the real image. This figure demonstrates the effectiveness of the method in accurately estimating camera poses, despite the dataset not having significant variations in scale and in plane rotation. Figure 14 presents the qualitative results of camera pose estimation on the ShapeNet Cars dataset. The first row displays the real image I and its corresponding deno feature F. The second row shows the best matching template feature F** operator, which indicates the estimated pose of the real image. This figure demonstrates the effectiveness of the method in accurately estimating camera poses, despite the lack of significant scale and in-plane rotation variations in the ShapeNet Cars dataset. Figure 15 presents the qualitative camera pose estimation results on the LSUN plane dataset. The first row displays the real image I and its corresponding deno feature F. The second row shows the best matching template feature F** operator, which indicates the estimated pose of the real image. This figure demonstrates the effectiveness of the method in accurately estimating camera poses, despite some challenges such as object articulation and partial observation, which are noted in the discussion of Figure 16. The overall precision of the pose estimation enables the generation of objects with complete geometry and the synthesis of comprehensive 360-degree views. Figure 16 illustrates the failure cases in camera pose estimation. These failures occur due to various factors such as object articulation, partial observation, and significant geometry differences. The inaccuracies in pose estimation could potentially be addressed by incorporating multiple templates, modeling additional degrees of freedom in camera pose, and disentangling geometry information during the matching process. Despite these failures, the overall distribution of poses remains generally precise, enabling the generator to produce objects with complete geometry and the ability to synthesize comprehensive 360-degree views. Figure 17 presents the uncurated qualitative results on the SDP elephant dataset. These results demonstrate good fidelity and diversity, showcasing the effectiveness of the method in generating high-quality and varied outputs for the given dataset. Figure 18 presents the uncurated qualitative results on the CompCars dataset. These results demonstrate a good level of fidelity and diversity, showcasing the effectiveness of the method in handling various car models and poses within the dataset. Figure 19 presents the uncurated results of camera pose estimation on the LSUN plane dataset. The results demonstrate a good level of fidelity and diversity, showcasing the effectiveness of the method in handling various camera poses and scenarios within the dataset. This qualitative evaluation provides insights into the performance and robustness of the pose estimation technique applied to the LSUN plane images. Figure 20 presents the uncurated qualitative results on the ShapeNet cars dataset. These results demonstrate a good level of fidelity and diversity, showcasing the effectiveness of the method in handling various car models and poses within the dataset. Table 6 provides a detailed runtime analysis of various processes involved in the training phase of the TeFF method. The template rendering process, which involves rendering the template feature field at discretized azimuth and elevation angles, shows a significant time reduction from the early stage, 0.0992 seconds per iteration, to the late stage, 0.0023 seconds per iteration. The phase correlation process, responsible for estimating the scale and in-plane rotation, takes 0.3898 seconds per iteration. Additionally, camera pose sampling, which includes calculating mean square error and performing inverse sampling, consumes 0.0156 seconds per iteration. These timings are crucial for understanding the computational efficiency and resource requirements of the TeFF method during its training phase. Table 7 presents the time analysis of the naive grid search method, focusing on the impact of different theta times phi-bin configurations on FIDGT and FIDIS scores, as well as the corresponding iteration times. The table shows that as the number of bins increases from 12 by 6 to 60 by 30, the FIDGT and FIDIS scores generally improve, with the best scores achieved at 48 by 24 bins. However, this improvement comes at the cost of increased iteration times, which rise from 0.0559 seconds per iteration at 12 by 6 bins to 1.3205 seconds per iteration at 60 by 30 bins. Despite the higher costs, the method with 12 by 6 bins still outperforms POF 3D in terms of FIDGT. Table 8 presents the evaluation of different numbers of bins for discretization on the FFHQ and AFHQ datasets. The azimuth theta range is set to 120 degrees, discretized into 36 values, reflecting the distribution prior for these datasets. Given the minimal elevation variation, the elevation angle is directly set to 90 degrees. The results demonstrate comparable performance with POF 3D on the FFHQ dataset and superior performance on the AFHQ dataset, as detailed in Table 9. Notably, despite POF 3D's strong performance in generated poses, their results degrade in ground truth (GT) poses. Our method achieves comparable results with EG3D on the AFHQ dataset, even without using GT poses, and only slightly lags behind EG3D on the FFHQ dataset. This analysis is further illustrated in Figure 11. Table 9 presents a detailed comparison of methods on the FFHQ and AFHQ datasets. The table includes metrics such as depthist, FIDGT, and FIDUS for the FFHU dataset, and FIDGT and FIDUS for the AFHU dataset. The methods compared are e.g. 3D, POF 3D, and ours. The results highlight the performance of each method in terms of depth estimation and image fidelity, providing a clear view of the strengths and weaknesses of each approach. Thank you for watching.